Hello students, once again back the property of the wave function. So the first property of the wave function which we have discussed was the physical significance of the wave function we have discussed was the probability. So we can say that probability is actually this wave function's modulus square. So wave functions, the important point is that the wave function provides directly the probability of finding the particle. So we have done it for one dimensional. We have done this pdx or maybe psi square dx, and if you integrate for minus infinity plus infinity, then it will provide the probability of finding the particle in whole 1D space. For 3D space, we do with this volume integral, because here is the only one. This volume integral contains dx, dy, and dz. So this will contain the whole universe. So after probability, now we discuss some of the other conditions. Normalization of wave function. So it's a very simple thing that normalization means is that we multiply the whole thing, we find out this probability, and once this whole probability is equal to 1, then this condition is known as normalization condition. Let me explain it. If the particle exists and we want to calculate the probability of finding the particle. Now, particle exists. It should exist anywhere. It can exist anywhere in whole the universe. If particle is there and you integrate this minus infinity to plus infinity with taking all the dimension, this dv contain x, y, and z from minus infinity to plus infinity. So it means that you are integrating this probability to finding the particle in all the universe. Definitely, if the particle exists, this whole number at least should come equal to 1, because somewhere in the universe the particle may exist. If suppose you integrate in this particular room, if you integrate for minus 2 millimeter to plus 2 millimeter plus 2 meter, because my room contains this 4 meter boundary, and it may happen that from minus 2 meter to plus 2 meter the particle may not be there. So my probability will come 0 if the particle is not in my room. But now, since you are integrating with respect to whole universe, so your probability is coming, which is must be equal to 1. Hence, this is the condition which is known as normalization condition. Once you integrate all over the universe, and there should be 1. So this is the condition, normalization condition, number 1. Second condition is the orthogonalization or orthogonal condition of a wave function. This is for two different things. Suppose psi m, the one wave function, psi n, the other wave function. And if we multiply two wave functions, so psi m is for m particle, psi n for n particle. The condition for multiplying, one should be psi m, second should be, obviously for the complex algebra, it should be the complex conjugate. So if we multiply psi m to psi n, the two different wave functions over all this space, and it comes out to be 0, it means this condition is named as orthogonal condition of a wave function. Normalization condition is for only one particle. Now there are two particles or the two wave function. So this condition is named as the orthogonal condition once this integration for two of the particle comes out to be 0. If you move from the expectation value number next, so expectation value is that similar which we usually called in our mathematics the average. So how you calculate the average? To get the average, suppose the quantity is q. Now I'll tell you this q is maybe the quantum operator also, but suppose my quantity is q. So what I'll do, I want to take average. This is the sign of average. So this quantity q should be calculated for all this one dimensional space. Suppose I am taking one dimensional. So what is happening? This is I am calculating this quantity. I suppose I want to calculate the age of all of you student. So what I'll do, I'll take age of each and every student. Okay. So and then we'll add age of all the student in our class. So what will happen? This q is to be calculated from minus infinity plus infinity. So I am adding because I am integrating, and then I am dividing this by total number of students age. This is what my condition. So this is I am dividing with the psi star psi, the condition. So this is what the total quantity divided by the total number. So this is what the expectation value of q, and in quantum mechanics we calculate the mean value or the expectation value in this manner. For example, for the position, I write this dx and x. So what I did in place of q, now I am taking x here. So this will calculate position for all the space divided by the number. And this will give you the x expectation value of x. Similarly, you can calculate expectation value of any other physical quantity. And if suppose this my function is normalized, as I discussed earlier, the psi star psi dx will be normalized, maybe it's normalized, and it should be normalized. If it is normalized, this quantity will be equal to 1. So my x will be only the addition of this quantity x. So expectation value will give you this. However, next moving further, we can also calculate the probability of finding the particle in a given limit. As I told you, in my room, I can calculate the probability of finding the particle in my room from -2 meter to +2 meter. So I can integrate this equation from x1 to x2. From this particular one, I can calculate the probability of finding the particle in a one-dimensional only in the x direction from x1 to x2. This is my limit. Some of the other conditions are the boundary conditions also. So the wave functions to satisfy some of the boundary condition. These all are very useful once we are going to discuss the Schrodinger equation application. So some of the boundary conditions are there. Psi must be finite. Definitely. It must be finite for all the values of x, y, z. Okay. So there must not be any infinite value. Psi must be well behaved. Well behaved means it should be single valued, because multiple values of psi will give you the multi probability, which is not possible. So it should be finite. It should be single valued. And number next, the psi and its derivative. For example, these are derivatives: psi, del psi by del x, del psi by del y, del psi by del z. So these all derivative must be continuous. So it's not that at any boundary, suppose I am moving from one room to another room. The particle is moving from one room to another room. So its wave function should also be defined in this room to this room. But at the boundary, psi and their derivative must be continuous. And psi should also follow the principle of superposition. We know we are targeting the group of wave for defining the wave functions. So that's why these all four boundary conditions are essential for psi. Next one is the eigenfunction or eigenvalue. We'll use this term now many of the times. It's very simple. Suppose we are having this wave function psi. I apply an operator. Now this operator may be dy by dx, for example. Here you also applied it. I'll tell you later on. But suppose this may be the operator. You are applying this operator on a psi. Suppose this is dy by dx, d by dy. Ultimately, it will differentiate my psi and it will give me psi prime. So psi prime is a function of the same variable. Now, if suppose I can define this psi prime as in form of psi here, but with this constant lambda. So it can happen. It will happen. Suppose I can take example and I'll take the example later on. So I am operating on psi. It will give me psi prime. Now what is the psi prime? Psi prime is now in form of psi with this constant lambda. So ultimately I can say that I am operating on psi and I am getting result lambda over psi. It means this operator will give me the constant lambda without changing the wave function psi. Psi is same, the left hand side and right hand side. In such cases, when I operate on a wave function, and my wave function remains same, then this kind of wave function is known as eigenfunction. O is operator, psi is eigenfunction, and lambda is the eigenvalue of a given function. I am repeating again that I am operating on a wave function, it will give me psi prime. Now I am writing psi prime in, suppose I take e to the power 2. So suppose I operate d by dx of e to the power 2. So I will get e to the power 2 once again, but twice here. So what I mean, if I operate d by dx on e to the power 2, I will get 2 into e to the power 2. So e to the power 2 will remain same here. e to the power 2x will remain same here. So d by dx of e to the power 2x will give me 2 into e to the power 2x. So my e to the power 2x is same. That psi is eigenfunction. Operator d by dx, I operated here d by dx. So my d by dx is my operator, and I got the value 2 here, and that value 2 is eigenvalue here. So this is also known as this eigenfunction or eigenvalue here. So suppose in this equation S psi equal to E psi, this is what the one form of Schrodinger equation also. So this S psi is E psi, it result me H is operator, psi is my eigenfunction, and E is my eigenvalue. So these all properties are very much essential to know the concept of a wave function. This all is very, very important. So we should know that what is the wave function. So these all are the physical interpretation of wave function, their properties. So we get to know from Vp, then we calculated Vg, which has provided me the group velocity, which is exactly equal to the velocity of the particle. So that's why we define this wave function in form of this particular equation in the exponential equation, and some of the physical significance like probability I have found it, then normalization condition, orthogonal condition, expectation value, some of the boundary condition, and this concept of eigenfunction and eigenvalue of the wave function. These all are the properties of the wave function. It should be known, and they are usually asked in the examination. From this particular basis, now we will shift to the derivation of Schrodinger equation in my next lecture.